So today what I'll do is I'll talk about some methods that are common in material science and try to show how they can be applied for biological analysis. Or rather, I'll let you figure out how they can be applied for biological analysis. So the outline of the talk, I'll talk a little bit about how optical choppers work. So they're a very common tool used in laser measurements. And then I'll talk about some classical material science measurement techniques, ellipsometry, photoluminescence. Is that better? Can you hear? Or is it? It's not on. All right, is that, yeah, okay, I can hear the echo now. Okay, so I'll be talking about ellipsometry, photoluminescence, and then some other advanced methods in pump probe, spectroscopy, and cavity ring down. So first, oh wow, it didn't show up. Okay, so first what I like to talk about is how to measure absorption. So in my slide, there's actually a blue cell here. I don't know why it's not showing up. But what we want to do is we want to measure the absorption that's passing through this test cell. And so the first initial idea that we have is, okay, we're just going to send a laser power P0. We're going to set that on the laser and then just measure on the detector P0, e to the minus alpha L. L is the length of the cell, alpha is the absorption in the cell. So what are the deficiencies in such a design? Say it again? Scattering. Okay, so scattering will tell essentially that we're going to lose power that's not due to absorption. Okay, so that's one concern that could happen. But thinking about how this is set up for measurement, what are some deficiencies in the measurement? Yeah. Say it again? I can't hear you. It's too near? Linear. Too linear. What's linear? I should go all the way up. Okay, so it's too simplistic because we just are assuming that it's attenuating e to the minus alpha L. Well, okay, so that's actually it's a reasonable approximation to assume that you're going to have some absorption per unit length. So that's an okay assumption that there's going to be a certain amount of loss per unit length. And the scattering effect that was mentioned can factor into that. And that won't be part of the absorption of the cell, but that'll be just the absorption or the loss as it's propagating. But thinking about how this is set up, what other deficiencies are there in terms of measurements? Like what can go wrong? What are the sources of error in this sort of measurement?
You're not measuring the initial.
Okay, so we're not set up to measure this initial power. Usually you set on your laser controller some power, 3 milliwatts. And you have no way of knowing that it's actually putting this out unless you measure it. So how it is now, you're just measuring what's being absorbed, and you don't really have a good sense as to what you're sending out. So the first thing that you can do, which is very simple, is just put a 50-50 splitter, break off part of the signal, and measure how much you're sending out. So now you have a measure of how much you're sending out, you have a measure of how much is going through, and you do a balance detection, which is essentially you're looking at, for example, you can take the, there are amplifiers that will give you the log of this. So you can take the log of these two, and there are other amplifiers that measure the difference, and so you can get the difference of logs, which will give you the ratio. So balance detection will allow you to correct for changes in the input power that you're sending. Okay, so very simple improvement. Now, this is still not an optimal way to do the measurement. So again, there's this blue test cell that didn't print. So let's think about other ways that we can improve it. And the easiest way to improve this sort of measurement is to chop the signal. So mechanical choppers are readily available in optics labs. They spin at a certain rate, and they have blades. So a typical chopper would look something like, I have a wheel, and then I have just a series of blocked regions. So as this thing spins, you're turning on and off the signal that you're using. And the reason that it's important to do that is because there are a lot of sources of laser noise. So the laser itself has inherent noise in it. The light output is not exactly 3 milliwatts. It fluctuates in time. Shown here is the intensity noise spectra. And if you look at it carefully, at high frequencies, there's a peak in the noise of a laser source. If you were to continue to measure this down to lower frequencies, you'd also see that there's a noise spectra for lower frequencies, and that there are things like 1/f noise. So 1/f noise, also known as flicker noise, can affect the powers that you see on your two detectors. Basically, the idea is that if I chop the signal, I'm going to narrow the bandwidth of which the noise can affect my measurement. So I'm going to measure in a very narrow band of the laser what's going to my two detectors. So the main idea is I want to filter out most of the noise spectrum of the laser and only have noise at one specific frequency, which is the frequency that I'm working with. And that'll allow me to get a much better result. So if I want to measure something in the weakly absorbing limit, so the factor alpha times L is much smaller than 1, then what I'm going to see is that these two signals are going to be about the same size. So I need to do very careful measurements to be able to resolve this factor e to the minus alpha L. So typical values for the absorption alpha L will be on the order of 10 to the minus 4. So with such a small value for the absorption, this is going to be within, these two are going to be, the ratio is essentially going to be 1 to within about 10 to the minus 4 of difference. So the lock-in amplifier allows you to do this. So the lock-in amplifier, the idea is that I'm going to modulate the signal that I'm sending to these two detectors, and what I'm going to do is I'm only going to read the signal at that frequency. Now that allows me to filter out the laser noise, and it gives me a better measurement. So in the chopper itself, there's a signal that comes out, which is a reference signal that goes to a lock-in amplifier. How many people have used lock-in amplifiers before? Okay, so only about 5 or 6. Okay, so the idea with the lock-in amplifier is that when you look at the signal that is coming in, you're going to have your signal, it's going to be some square wave because you're chopping it, but there's going to be a bunch of noise on it. So this is your signal that you're sending to your lock-in amplifier, and what you're trying to recover is you're trying to recover the underlying pattern that's in the signal. Now to do that, what you need to do is you need to be able to know at what frequency to filter. So the lock-in amplifier always consists of two inputs. There's the signal input, and there's also the reference. And the reference input needs to have the same frequency as the signal. It needs to be phase locked with the signal. It doesn't necessarily have to be in phase. So I could have something that's at the same frequency, but let's say it's slightly out of phase with that signal because there's a different delay, but these two things are at the same frequency. So these signal and reference go into the lock-in amplifier, and in modern lock-in amplifiers, they use a lot of digital signal processing to get the signal recovered, so essentially from this noise, to recover the underlying peak-to-peak amplitude. The way that the optical chopper does this is that internal to this motor, so there's a motor that's spinning this around, there's the laser beam that passes through one part, and so as this spins, it's going to generate an internal reference signal that it converts to an electrical signal because there's a photodetector here, and this photodetected signal goes to your lock-in amplifier, and that's the reference. Does that part make sense? So please ask questions as we go along. I want this to be interactive.
Why doesn't it matter that the reference is out of phase with the
Okay, so they can be out of phase because in your digital signal processing, so what may happen is, let's say the length of this cable is hundreds of times longer than the length of this cable. So when the signals arrive, they're shifted in terms of their time. So you can't necessarily control them to be exactly in phase. So what the lock-in amplifier does is it compensates for that phase difference. So what it'll measure the peak-to-peak amplitude, and it'll also measure the phase difference between the reference and the signal. So those are the two main outputs that it'll give.
Why can you only measure weakly attenuating samples?
Well, this is, so if you have a strongly attenuating sample, you don't need to do as many of these tricks. So if your signal is alpha L much bigger than 1, then this is going to be significantly different than that, and it'll be very easy to make the measurement. The ratio will be very far away from 1. But if they're very close, like it's weakly attenuating, then you have to do a lot more tricks.
So
So the reference here is shown as a perfect clean signal, but you're also measuring it from another photodetector
Right.
that has noise on it.
Right. So it's shown as a perfect signal, but in general, so there is noise, but the noise is generally much smaller than the noise on your signal. So that's the main idea, is that you're making this measurement, or the reference signal is coming about based on something that's local to the motor that's spinning, and this is very low noise. Whereas this measurement for these detectors, they're passing through air, they're passing through samples. There may be higher noise for those photodetectors. Other questions so far? Okay, so let's look at what the lock-in amplifier does. So what I have is a LabVIEW program which kind of demonstrates what it does. Basically, it acts as a very narrow bandpass filter. So it filters out all the other frequencies and allows you to recover your signal. So for example, when you look at this curve, can you tell that there's a 3-volt signal buried in this noise, which is like hundreds of volts? With your eyes? No. There's no way you can see that. But it can actually recover and say that there's a 3-volt signal. So the way that this is done, so let me pull up the LabVIEW program and run this. Okay, so what I'm showing here is, so I've switched from a square wave to a sine wave just so that it's clearer that you can tell the difference between the reference and the signal. So now what I'm doing is, instead of having my signal be a square wave, I can think of it as a sum of different sine waves. So let me just look at one of the frequencies of the sine wave for my signal. My reference is still going to be a square wave. So what I'm looking at is, this is my signal. So I set up a 10-volt peak-to-peak signal, 50 hertz repetition rate, and it has a specific phase, 30-degree phase, so it doesn't start off at 0, it starts off at part of the way through the sine wave. What's not shown is the reference. So this is my signal. In the reference, what you're looking at is, so this is, let me open this up. So this is the signal that I have, so I assume that I have a very large signal, and this is my reference. So you can see that there's a tiny bit of noise that I put on the reference. And the phases of the two, they're not exactly in phase, but the phase difference is not changing in time. So whereas the red curve, which is the data curve, you pass through 0 here, which is the 0 part of the phase, the white curve, which is showing the reference, doesn't turn on until 30 degrees out of phase. In comparison. So these two signals are 30 degrees out of phase. So what the lock-in amplifier is going to do is, from the reference signal, it's going to figure out the frequency. So the goal of this filtering algorithm is, I need to know the frequency and the phase of the reference signal, and then what I'm going to do is, I'm going to synthesize a sine wave at that same frequency with that same phase, multiply it by the data signal, and use the fact that sines and cosines are orthonormal. So I'm going to use the completeness of sines and cosines as basis functions, and I'm going to express this sine wave as a sum of different sines and cosines at different frequencies. So I'm using Fourier Analysis. So what I want to do is, I want to figure out what is the amplitude and frequency, what is the amplitude of this particular frequency sine wave that I generate based on the reference. Questions on that? Is that clear, like what I'm trying to do with it? You guys okay? Okay, so I generate the sine wave. The sine wave is at the same frequency, so it's not this. The red one is the data that I have. This white curve, I generate a sine wave at the same frequency and the same phase as the white curve. I multiply it by the red curve. I also generate a sine wave that's 90 degrees out of phase, so I generate a cosine wave. I multiply it by the red curve, and from those two multiplications and averaging, I can figure out the amplitude of the original data signal and filter out the noise at all the other frequencies. So what that looks like in the demo is, okay, so I have this data signal, and I set my amplitude to be 10 volts. I generate my matching sinusoidal signals, and I can calculate, so these quantities x and y. This is the in phase, and the other one is the quadrature components of this multiplication. And what I recover, this amplitude, is the sum of the squares of x and y. So this amplitude is basically agreeing with the amplitude that I set in, and the phase that I recover is the difference in phase between the data signal and the reference signal. So this is the initial demonstration where I have very little noise. So right now I only have 0.1 volt noise on a 10 volt signal. As I increase this, so if I go up to 1 volt of noise on a 10 volt signal, you can see that there's still the sinusoidal pattern, and you can recover the amplitude is still 10 and the phase is 30 degrees. As I start increasing this more and more, I can still see that it can recover the signal. So if I have signal to noise ratio of 1, from this I can still determine that the amplitude is still 10. And I can show what the recovered signal looks like. The recovered signal on top of that is that red curve. And so that's basically saying from this gray set of noise that I measure, the red signal is my true underlying wave function. So I can keep increasing this, and this starts to get interesting when I have, so right now I'm at a signal to noise ratio of 1. So I have equal amounts of noise as I have signal. If I go to a signal to noise ratio of 0.1, normally you talk about signal to noise ratios greater than 1. So if I have signal to noise ratio of 0.1, what that's saying is that the noise is 10 times the signal. And you can still see that I'm recovering the amplitude with this method of about 10, and the phase is still relatively accurate. At the bottom, what I'm showing is the frequency domain representation of the signal. So as a function of frequency, you can see, well, it's kind of obvious that if I have a peak at 50 hertz and I can filter out all the noise at all these other higher frequencies and these lower frequencies, that I should still be able to get a relatively good estimate. So it's kind of obvious that if I just did a frequency domain analysis, that I'd be able to recover the signal. Now, that's not the case if I keep increasing the amplitude. And this is one of the noise. And this is one of the key points as to why the lock-in method is really good, is because I have a clean reference signal. So right now I'm at a signal to noise ratio of 0.1. If I go to a signal to noise ratio of 0.01, so I have 1,000 volts of noise and a 10 volt signal, now you can see that the frequency domain, there's no dominant feature. There's sort of a little tiny peak here at the 50 hertz, but it can still recover relatively. It's not perfect. If I average for longer, I'll get better results. But you can see that I'm getting like numbers like 4, 7, 16. If I average those numbers for enough runs, so this is taking like 100 milliseconds, if I average this for more time, I can still recover my original 10 volt amplitude, even though I don't see it in the frequency domain. So the reason that it's different than just a frequency domain analysis is because I'm using the reference to figure out what frequencies to work with, and the reference is assumed to have low noise. In the signal, if the signal has a ton of noise, so if my signal is doing something like this, and I have a ton of noise, I can't really tell what frequency I have in my signal because the noise is overwhelming it. But if I have the frequency correct in the reference, then I can filter and recover the signal back in the original time domain plot. And I can recover that value of 10. So this method in general, you can recover signals from the noise when you have signal to noise ratios on the order of like 10 to the minus 3, 10 to the minus 4. So it's a very sensitive method. And what I talked about with the optical chopper is equally applicable to this analysis. It's just that you have to think about multiple frequencies rather than just one. So the lock-in amplifier, the goal of it is to be able to recover signals from noise. I should probably stop the lab view so it doesn't tie up resources. All right, any questions on lock-in amplifiers? Do they make sense as to why you would use them? Sure? Okay. So the choice of frequency. So I was operating at 50 hertz for the demonstration just because of time. But what you should look at is, well, I'm free to spin this motor at whatever rate I want to spin it. Normally the rates that commercial instruments can go through are on the order of 1 hertz to about 4 kilohertz. That's sort of the typical range based on how fast they can spin it and how many blades they can put in a single wheel. And actually, for most choppers, they actually put 2 wheels that are on top of each other, and these have different periods. So usually, you can have 2 different frequencies of operation from a single reference. So although I have the reference at 1 frequency, I know that the frequencies for the inner wheel and the outer wheel are related to each other because of the number of spikes that the blade has. And so I can figure out the frequency of the outer part and the inner part if I just know one of them. So when you pick your frequencies, it's very important to think about the noise spectrum. So if you look at the noise, there are typical fluctuations that occur every day. It gets hot, it gets cold, morning and night. There are fluctuations that occur on a monthly basis and an annual basis. So at those frequencies, those have a lot of noise. So you don't want to chop your signal at those frequencies because they're very high noise. 60 hertz is the frequency for electrical signals, so there's a peak in the noise there. 120 hertz, typically you get the double of the frequency. So you get harmonics of 60 hertz. So 120 hertz is a bad frequency, 180 hertz is a bad frequency, and so forth. Traffic signals, there's actually a peak at 500 hertz. And then you have things like, if people are still using cathode ray tubes, you have peaks in the other part of the spectra. So where should you pick the frequency for chop? Obviously you want to go as low of a noise as you can, but you're limited by your measurement apparatus. So when you look at this setup, you need to be able to, one, mechanically chop that fast, and two, your photodetectors need to be fast enough to record the signal. So typically people will pick in the range of like 1 kilohertz or up to maybe like 3 or 4 kilohertz. Those are the most common frequencies used for chopping, and it's based on the noise spectrum. My suggestion, I like to pick prime numbers so that it's not a harmonic or a subharmonic of specific frequencies. Okay. The next topic that I'll talk about is ellipsometry. So optical choppers, that's sort of a baseline thing. People use it in addition to a lot of these other methods. So in ellipsometry, the idea is that you want to measure the thickness and the refractive index of a material. So you want the real part of the refractive index, which tells you how it bends light, and you want the imaginary part, which tells you how it absorbs. The way that it's done is that you measure a polarization. You measure the reflection for two different polarizations and compute that ratio at various incident angles. So a picture, wow, all my colors are off, and these were different colors in my slide. So you have a light source, and this light source starts off sending out all the different polarizations. So it's a single wavelength light source, or it could be multiple wavelength, and you resolve it in terms of P and S polarization. You put in a polarizer such that you get a linear combination of P and S polarization, and you launch it at some angle relative to the sample so that what comes out is elliptical polarization. That's why it's called ellipsometry. So you get elliptical polarization out. You have an analyzer, which is typically a rotating device that's going to select one of the polarizations, and then you measure it either with a monochromator if you had a broadband light source, or this would just be a photodetector if that were a tunable laser. So the signal that you're going to measure the ratio of the reflection from the P and S polarized lights. And you're going to write it in a form where it's tangent of some variable psi and some phase e to the I delta. So this is going to be what you record, psi and delta, and what you're trying to find is n, which is the real part of the refractive index, and kappa, which is the imaginary part. So you want to understand how the film behaves based on how it reflects these two signals. So you fit psi and delta. Usually you collect this for many different wavelengths, and then you fit it to some model that's going to describe how the refractive index and the absorption coefficient change as a function of wavelength. So you measure this at many different wavelengths. You get these values for psi and delta as a function of wavelength, and then you solve for n and kappa. It's actually shown here how you do it. If you have a very thin layer, these are the formulas for reflection from S and P polarized light. You can see that they're kind of complicated with square roots and so forth. And this n tilde is what you're trying to solve for, which has the real and the imaginary parts. So if it's a thin film, you can use this formula. From what you measure in this ratio, you can solve for n tilde from what you measure. The problem is if you have a multi-layer stack, if your thing doesn't just have a single reflection, then you have to worry about interference. Is there an eraser? I should have looked for the, no eraser. Looks good. Thank you. So the problem comes in, so it's simple if you have a very thin film. The idea is that when you send the light in, you look at this reflection, and the reflection from this interface and from this interface are pretty much coming together. Like if you have a thin film, you just think of it as just one reflection. If you have a thicker film, then you have to worry about these two reflections interfering. So the way that you have to do it in this case is that you have to model this as a multi-layer stack and calculate what the reflection coefficient will be for the two different polarizations, and typically you use some numerical method to do that. Yeah.
What are the sizes for thick and thin?
Thin would be something like, so it's all in comparison to the wavelength. So usually you scan the wavelength from, let's say, 280 nanometers to 1700 nanometers. So thin would be something like lambda over 10 or 20 or something. So on the order of about 30 nanometers. And then thick would be bigger than that. Yeah. Other questions? Okay. So this is some typical data. So this is a picture from MRL, so Materials Research Lab on campus. You place your sample, there's a light source. The light source is on a rotating stage. So at different angles, you're going to measure the reflection off the sample. This is a glass sample with a thin layer of palladium on it. And this is the data that it generates. So as a function of wavelength, and for whatever reason, some of the plots are in angstrom, some are in nanometers, but you measure the psi, which tells you the amplitude ratio. So if you look at this, tangent of psi tells you something about the amplitude, delta tells you something about the phase. So you measure this at different angles of incidence. You measure the amplitude and you measure the phase, and from that you fit it to a model. So there's some model for your n as a function of wavelength and kappa as a function of wavelength. Based on those parameters in the model, you match these two curves. The problem is that there are too many free parameters if you were to say that n and lambda or n and kappa can be any value at any different wavelength. You have to assume something like there's a smooth transition or some smooth shape for n and for kappa because there's too many free parameters. So once you do this fitting, so the setup, you have tunable tunable monochromator that covers 240 to 1700. You can measure angles of incidence from almost normal incidence to almost flat. And this is actually temperature dependent. So you can set it to run at different temperatures, from very low temperatures through room temperature and even at elevated temperatures. So from this, you can calculate n and kappa from that fit. So that's the general idea with ellipsometry. Questions on ellipsometry? Okay, so let's get into photoluminescence then. So photoluminescence, biologists I guess would call it fluorescence. What you do is you excite the sample at one wavelength and then you observe the de-excitation or the emission at a different wavelength. So what you have under your control, you can control the energy of the signal that you're putting in. You can, so like what wavelength you're exciting it with, the intensity of the sample or of the power that you're pumping with, and then the temperature of the sample. And then when you look at the spectra that you get in the luminescence, you're looking at things like the peak position, the intensity, the full width half max. And there's a lot of things that you can get out of that sort of information. A lot of this stuff is semiconductor related, but there are comparable quantities for biological samples. And then there's another method, which is to do time resolved photoluminescence. So you excite the sample with one wavelength, you wait a fixed amount of time, and then you look for emission at a different wavelength. It's more complicated than steady state, but you can get a lot more information if you time resolve it. So this is a typical setup for what photoluminescence looks like. I have a light source, and again, you will chop the signal. The reason that you have to chop the signal is, okay, so I send my light source, let's say at 400 nanometer light source. It hits the sample, and then it starts emitting at 1100 nanometers to 1500 nanometers, depending on what sample it is. And then the emitted light goes in all of these different directions. It's uniformly emitting in multiple directions. Your laser signal may bounce back. There may be some scattering from other things that make it to your detector. So you chop the signal because the emission from this is going to be very, very weak. So you want to be able to recover a weak signal in the presence of noise, such as room light, So you chop the signal that you're pumping at a specific frequency, and then this should emit at that same frequency. So if I'm modulating this on and off at 1 kilohertz, this should be luminescing on and off at 1 kilohertz. Some of that signal is going to make its way through the lens that you're going to collect, and then you're going to measure the spectrum of it, and you're going to put your photodetector connected to a lock-in amplifier because you want to make a low noise measurement, because the signals that you get are very, very weak. So the energy diagram of it is simply you have a valence band and a conduction band, and the photon that you send in from the laser source is going to excite a carrier to some excited state. There may be some non-radiative relaxation to some other state in the conduction band, and then from there you're going to emit your light signal, and this luminescent signal is what you're going to use to figure out information about this energy transition, how many bands you have, how pure of a material you have, because if I have a lot of different types of materials next to each other, I'll have different energy bands. So what I'm looking at is the width of this will tell me information about how pure my bands are, and it'll also tell me information about doping and a lot of these other parameters. So these are our typical photoluminescence plots. On this particular sample, there's a active region for a laser that emits around 1450 nanometers. There's some other layers in the material that emit at 1100 nanometers. So from the information about the amplitude and also the width, you can tell things about the quality of the material that you have. And then this is a picture from MRL of their photoluminescence setup. Some of the luminescence can be polarization dependent. So the idea is that if you align the polarization of your light source with the crystallographic directions of the sample or of the bonds between the various atoms, you can get different emission patterns. So depending on the alignment, so this is for one alignment and this is for another, you can get different intensities. So this can tell you information about the structural composition of your material. Okay, questions about photoluminescence? Yeah.
As a reference frequency for your locking amplifier, you would use the frequency of the chopper? Or?
Yes, so you would chop at 1 kilohertz, and the chopper, so I didn't show it, the chopper has an electrical signal that connects to the lock-in amplifier. So you have a square wave reference signal that's going to the lock-in amplifier. Your photodetector here is going to see a square wave signal based on the fact that you're chopping it. Other questions? Yeah. Yeah, so probably 1 kilohertz would be more common. So the trade-off, so I mentioned that you can either do like 1 kilohertz or 3 to 4. As you spin the chopper faster, you start to get mechanical vibration. So people avoid that based on the mechanics of it. From the electrical standpoint, it's better than at 1 kilohertz, but the mechanics of how the chopper spins gives you some additional noise. So I would say 1 kilohertz is probably your best choice for frequency.
These are mechanical.
Oh, okay. So one of the things I should mention is that when you chop at these high frequencies, so I didn't, the number of spikes that you have going around the ring, typically the blade will have like 60 grooves going around. So you're really spinning the thing at something like, so 1 kilohertz, you'll be spinning at maybe 16 revolutions per second. So it's not that fast, but it's still pretty fast. Like you can feel a breeze coming off of it. So you have to compensate for that. Like you don't want it to blow your sample and cause mechanical motion of your sample. Yeah.
What's the advantage of using the chopper over modulating your laser?
When you modulate, so that's a very good question. When you modulate your laser, so you're turning it on and off. So some of the issues that you can have is the wavelength can change based on heating. So when the laser's off, it cools a little bit, and then when you turn it on, it heats up a little bit. That temperature change can shift your wavelength. So if you look at turning on and off, one, you don't get perfect extinction. So when you turn it off, it doesn't go exactly to zero. Well, I guess it goes mostly to zero. But two, the wavelength during the pulse can change. So as it heats up, it changes the wavelength. And that may be okay for some applications, but for a lot of things with spectroscopy, it's not a good thing. So the alternative way people do it is they have a CW laser and they have an electroabsorption modulator. And the electroabsorption modulator is outside of the laser cavity, and so you can turn that on and off as fast as you want without affecting the performance of the laser. So it's like a chopper, except it's an electrical version of it. Other questions? Okay, so let's talk now about pump probe type measurements. So in pump probe, there are two versions of it. One is a time domain pump probe. The second is a frequency domain pump probe. So the time domain pump probe is sort of the easier one to understand what you're doing. So you have some device under test. This could be your sample. It could be, it's basically your sample. And you're going to send pulses to excite it. That's the pump signal, and then you're going to watch how that excitation changes its response with the probe signal. So you put it in an excited state with the pump, and then you probe it sometime later. So there's a delay between when you pump it and when you observe it. And these pulses can be optical, electrical, and what you measure coming out can be pretty much anything. It could be absorption, it could be changes in reflection, it could be photoluminescence, a lot of things that you can look at in terms of what's coming out. But the key principle is I'm going to pump it with usually a very large amplitude. So you think of the pump as very, very large amplitude in comparison to the probe. The probe is generally going to be weak, so I show this as like 10 to the minus 3 of whatever this is. So the probe is going to be very weak, and you're going to have a delay between the two. So you excite it at time t equals 0, you're going to probe it 2 microseconds later, 2 femtoseconds later. It depends on how fast your system responds. So a typical response will be something like this. If I send my probe before I send my pulse, I shouldn't get any change in my signal because my probe is very weak. So if I probe it before I excite it, I should have no change. As soon as I probe it after I excite it, I should see a large change in my output, whatever the output happens to be. And then as the system naturally relaxes and loses energy, then the signal that I get decays, and it's usually some sort of exponential decay. So the idea, I pump it at one time, and then I probe it at some other time. If I probe it before I pump it, I get no change. If I probe it after I pump it, for a short moment in time, I'll get a very large change, and then I'll get a decay as this returns back to equilibrium. So some of the assumptions that go into this measurement, one, the pump is responsible for exciting it. The probe needs to be very weak. So I don't want when I probe it that this probe excites it also. I want the probe to be a way to see what state the system is in. So the probe needs to be very weak. Two, the width of these pulses needs to be short compared to the response time. So if I look at this response time, if it takes, let's say, 0.15 picoseconds for this to respond back to equilibrium, this width for the probe or for the pump and for the probe needs to be very small in comparison because I want to be able to excite it and then watch it decay. I don't want to be continually exciting it while it's decaying. So I want to excite it at one moment and then watch it decay. So the width of these pulses needs to be very short so that my system is what's known as temporally resolved. And then the third condition is I want the system to go back to equilibrium before I excite it again. So it's shown here, this is like if I excite it and it takes 0.15 picoseconds to recover, then I want to wait maybe several times this, so I'll wait like 1 or 2 picoseconds before I excite it again. So I want it to be back into equilibrium before I excite it again. Does that make sense? Okay. The second type of pump probe, and I should mention that this pump probe is available at Materials Research Lab. They have femtosecond lasers that can generate these narrowband pulses, and you can do this sort of time-resolved measurement. The second type of pump probe is now in the frequency domain. So now, unlike the previous case, these are continuous signals. So I'm always applying this signal as a function of time. What I'm doing, though, is one signal is at one frequency, the pump is at one frequency, and the probe is at a different frequency. So what I'm looking at are resonances. So the way that this is typically explained is, imagine that I have a 3-state system. I'm going to use the pump, so I tune the pump to some particular spot. the pump is going to excite the transition to state 2, and then if I keep pumping it, all I'm doing is exciting up to state 2. The probe, however, will allow us to measure how excited the state is by looking at the decay to some other level 3. So I tune the frequency for the probe to this energy difference. So when this difference between pump and probe matches the difference between these energy levels, then I get a peak in terms of my emission at that frequency. So if I match these things up, if the frequency difference between pump and probe is the difference between these 3 energy transitions, I'll get a peak at that one frequency. And as I detune my probe compared to that match, I'll trace out, usually this is some sort of Lorentzian type curve. So this allows me to figure out, 1, the center energy for this sort of transition, and 2, the width of the transition, so I can look at things like thermal broadening of my energy levels. So the assumptions here, both signals are continuous, but they're operating at different frequencies. As before, the probe is much weaker than the pump. Now there's one new condition for frequency domain. I need it to be frequency resolved. What that means is that the width of these pulses, the width of these signals needs to be small in the frequency domain compared to what I'm trying to measure, which are these energy level differences. So there's going to be some fluctuation or some, not fluctuation, there's going to be some broadening of this energy level. It's not an exact single energy. There's going to be some broadening. So what I want to be able to do is I want my resolution in the frequency domain for these signals to be small compared to the broadening of these energy levels that I'm trying to measure. So I want to have a frequency resolved type measurement. Okay. Any questions about pump probe? Yeah. Yeah, you can think of this particular transition as the pump is being absorbed and the probe is causing stimulated emission. So that's one application of it, that you're trying to de-excite the higher energy state, and by looking at the emission at this frequency, that's the signal that you're trying to measure. Yeah. Mm-hmm.
What kind of light sources do you use?
For these, it's typically a tunable laser. So you'll have one strong CW laser, and you want it to be tunable because you want to have this particular transition matched. So you have one strong tunable laser to get to that frequency. You have a weaker tunable laser because you need to change the frequency. Yes?
Thinking about white light probe,
Mm-hmm.
Is it possible to get particular emission only like a particular wavelength?
Yeah, you can use a white light. So the common question that I get asked is, okay, instead of a tunable laser, can I just use a white light source and a monochromator? Yes. So a white light source plus a monochromator generally gives you equal or the same types of information as a tunable laser. The trade-off is usually that the white light source is not as powerful, so you generally don't get enough signal for the white light source. And then the resolution that you can get with a monochromator is generally not as good as the resolution you can get with a tunable laser. So with a tunable laser, for example, I can set the laser wavelength accurate to like 1 picometer. Whereas if I try to measure with a monochromator, a typical resolution would be something like 100 picometers. So I usually get better resolution with a tunable laser, and I get all my power at that one frequency rather than wasting it over the band. But but tunable lasers are more expensive, so it's a trade-off in terms of cost and how you run your system. All right, so so now let's talk a little bit about spectroscopy. So chemicals have unique infrared signatures. So shown here, these are the absorption spectra for carbon monoxide, NO, and methane. So different wavelengths, you get these peaks in absorption, and these have to do with the rotational and vibrational motions of the atoms. So what we want to do, for example, is measure the absorption. So I'm going to kind of skip this slide. Basically, the idea is that if I look at the spectrum in one of these graphs, which is known as sigma, you get an actual spectra. In the other graph, which is known as S, it's basically the integral of sigma over some bandwidth, so I just get lines. So I'll kind of skip this because it's not as important. I'll kind of skip this also. Basically what we're trying to do is we're trying to measure these peaks. So we want to see at a specific frequency, is there a signal? If there's a signal, then that means that there's that particular type of gas in our mixture. So as I change the wavelength of the light source that I have, if I see a sudden increase in absorption, and I correlate that with the known absorption spectra, I can figure out that I have a specific type of gas. This type of measurement, usually these absorptions are very weak. So I have things like alpha L much smaller than 1, even when I have like a 1 meter long absorption cell. So what I need to do is I need to use some of my techniques to be able to get measurements of very small quantities. So I'm going to be battling the problem of large amounts of noise and low signal to noise ratio. So the idea is, again, I have my test cell here. And now what I'm trying to do is, because I'm trying to measure this spectrum, what I want to look at is, when I change the wavelength, how does the power change? How does the signal that I get go through? So what I want to do is not turn on and off the laser or turn on and off with a chopper. What I want to do is have a continuous laser and turn the wavelength up and down. So I have some fixed wavelength. What I want to do is modulate the wavelength back and forth so that I look at changes in the transmission, because the absorption depends on what wavelength I'm at. So I'm moving the wavelength back and forth, looking at the change in transmission. So my setup looks like this. I have my test cell here. I send in the signal. Again, I'm going to split half and half. The first detector is just going to tell me how much power I'm putting in. The second detector is going to tell me what's being absorbed. But now what I'm doing is I'm changing the wavelength that I'm sending in. So I don't have a chopper in this picture because I'm not turning on and off the laser. I have a CW laser, but I'm varying the frequency. So if I look at what this is going to do, I'm going to still have my lock-in detection the same way as before. I have a reference signal which is telling me how fast am I moving the wavelength back and forth. And what I'm going to do is, so I'll first explain this where lambda 0 is constant. So let's say that lambda 0, which is my center wavelength, so let's say that I sit here. Because what I'm looking at is, I want to sit at some fixed wavelength, move it back and forth so I see a change. So I'm going to sit at one fixed wavelength, move it back and forth. I'm going to move to a different wavelength, move it back and forth. Move to a different wavelength, move it back and forth. And what that's going to tell me is places where I get a large change from moving it back and forth, those are places where this is going on a slope. At this center point, when I move it back and forth, I'll get no change because I'm at a maximum in my absorption. So I need to be able to modulate the frequency of the laser. So the wavelength that I'm sending out is going to be modulated back and forth. So for example, it's going to be at 4,000 nanometers, and then it's going to go up to 4,001, go back down to 3,999, go up and down in terms of the wavelength. And then the center point is going to be slowly shifting so that I can figure out, or I can trace out this sort of response. So let me show another picture of what this is doing. So this input is, I have a CW signal, I have a fixed amount of power, I'm sitting at one wavelength. The output that I get depends on the absorption. The absorption depends on the wavelength. So the output that I get will change if I change my input wavelength. So if I modulate the wavelength back and forth like e to the j omega t, so I put the sinusoidal modulation on, the output I get, I can write as a power series or a Taylor expansion. It's going to be involving a sum of derivatives times how far my input is varying from my center wavelength. So I'll get modulation in my output. And the idea is that when I plug this formula into my output, I'm going to get a power series, and now the modulation is not going to occur at frequency omega m, it's going to occur at n times omega m. So what that means is that if I modulate it at one frequency, if this function is purely linear, the output I'll get will be at that frequency. If this function is quadratic, then I'll get the output at double the frequency. So I create harmonics at different frequencies, multiples of the frequency that I'm driving it with, and those harmonics will tell me information about the derivative of the curve that I'm measuring. So I can figure out not only the value of the curve and its slope, but I can figure out all the derivatives by looking at the frequency spectrum and looking at what the signal is at these harmonics. So the lock-in amplifier, usually this is a digital device, I can record the signal at the first harmonic. That's what I explained before. So I create a reference signal, I look at what my real signal is at that frequency. Because this is done digitally, I can create signals at double the frequency, at triple the frequency, and all the other harmonics. And therefore I can calculate what the derivative of my transfer function is, my output function as a function of input, I can calculate all these derivatives using the digital lock and amplifier. So looking at the nth harmonic, I get information about the nth derivative of my signal. And then we repeat this, so I do this measurement, I get all the derivatives at that one spot, and then now I move the center spot to a different spot, and then I go back and forth at that other wavelength being the center. From this, what I'm trying to figure out is, I'm trying to figure out at what frequency or what wavelength is this thing a maximum? Because if I know the wavelength, then I know what type of gas it is. Different gases have different wavelengths that have absorption peaks. So I need some way to figure out where is the maximum wavelength. And so the simplest way is just say, okay, if I look at the first harmonic, if I'm at some point here, the first harmonic is positive because the slope is positive. At the peak, the first harmonic is going to be 0 because I'm at a point I'm at a maximum. And then here, if I modulate it, then because the slope is negative, the first harmonic will be negative. So as a function of the center wavelength that I put, I'll have a positive signal here, I'll have 0, and I'll have a negative signal. So if I just look for the place where it goes from positive to negative, that tells me the wavelength that has the peak. The other way to look at it is to look at the second harmonic. So if I look at the second harmonic, if this is some Lorentzian type shape, if I look at the second harmonic will be maximum at this peak location. So certain types of line shapes, the second harmonic, which tells me something about the second derivative, if there's like a point of inflection, the second derivative would be 0. But here where I'm at a maximum, the second derivative will be a maximum. So usually people look at the second harmonic. And the reason they look at the second harmonic is if I look at the first harmonic, there can be ways that my signal, so if I modulate this at one frequency, there can be noise coupling between the way that I'm modulating this and how these detectors are responding. But if I modulate this at one frequency and I look at the second harmonic, so I'm looking at a different frequency than what I'm modulating at, this is going to tell me something about the nonlinear properties of this test cell. And that's going to be the way that I figure out the absorption peak location. So most people will use the second harmonic because there's noise coupling for the first harmonic. Okay, questions about wavelength modulation spectroscopy? Okay, there's another method which is frequency modulation spectroscopy. The point of this is that if you look at the noise in terms of this, so what this requires is a laser that has one fixed wavelength. So if I look at the signal, what I want to do is change it back and forth without having a lot of spreading in terms of the frequency or wavelength that I'm launching in. There's this known plot, which is the frequency noise. And basically what it says is if you operate at low frequency, the noise, so if you modulate a laser back and forth in terms of its wavelength, the noise that you have is bigger if you modulate it back and forth at a kilohertz rate compared to if you modulate it back and forth at a gigahertz rate. So if I do high frequency modulation of the wavelength, then I can get lower noise. So this kind of explains the frequency modulation technique. Okay, the last thing that I was going to cover is cavity ring down. And the idea, oh, you can finally see my slightly pink cavity. So the idea with cavity ring down is I pump a signal at, I send in a pump signal which is a pulse signal, and then this is going to bounce back and forth in the cavity. The first pulse that comes out initially, and it has high amplitude, and then subsequent pulses come out and they get weaker and weaker because as they bounce back and forth in this cavity, one, there's a certain amount of loss from these two mirrors. Two, there's a certain amount of loss per unit length. So when I look at the output, I can write it in this sort of form. The key point is if I look at the amplitude of this peak compared to this peak, this ratio is going to be proportional to the reflectivities on the two ends of the cavity and the loss alpha or the round trip loss e to the minus 2 alpha L. So this again can apply for optical pulses, electrical pulses, acoustic pulses. This is sort of a general technique. The idea with this is, again, we want to measure the loss alpha, but we put it inside of a cavity because it's a more sensitive measurement by putting it in the cavity. Basically, the light will interact with the media for much more paths compared to if I didn't have the cavity and it just passed through one time. So when I look at this, what I'm going to do is I'm going to fit the amplitudes of each one of these peaks to this sort of functional form. Every additional peak should be multiplied by a geometrical factor. So I'll get a geometric ratio with this as the factor. So if I plot this as a log plot, I'll get a linear relationship. And from that slope, I can figure out that the factor for the cavity, R, and then the loss is 0.8. What I'm trying to do is I'm trying to solve for this loss term. So if I look at a regular graph, it'll be an exponential decay in terms of my amplitude. Now, in order to figure out the loss part, e to the minus 2 alpha L, and separate it from the cavity, I need to reference this. So I reference it compared to an empty cavity. So I need to build an identical cavity to my test cavity where I don't have any lossy media in it. If I do this, I get the same results, except instead of having that e to the minus 2 alpha L, that term is gone. So this allows me to measure the reflectivity. So I again fit the data. The red curve is the empty cavity, so no loss. When I put the lossy material in, I get a slight change in the slope. Basically, it decays slightly faster because I have that additional amount of loss. So if I go through and I do some error analysis, you'll see that I can measure very low losses. The problem is, even if I'm measuring accuracy of something like 2 times 10 to the minus 3, my errors are going to be a factor of 50%. And that's because I'm trying to subtract two very small numbers. So this method is useful, but you have to be very mindful of using error analysis correctly, because the errors that you get are actually, or the uncertainties are actually pretty large when you subtract two numbers that are close to each other. Okay, so then this is used for gas absorption, strain sensors, and this is also used for optical waveguide loss measurements. So in conclusion, basically a lot of these techniques that I explained, they're available at Materials Research Lab. They're available in some professors' faculty labs or in MNTL. And their main advantage is that they're generally non-destructive. So when you do an optical method, you're generally not killing the sample that you're working with, provided that the power is low enough. Okay, so with that, I'll end the talk and ask if there's any questions. Just trying to draw out a clap from the audience. So, questions? I guess you guys asked them all during the talk. All right, so I think you guys are free for lunch now. And I'll stick around if you have any additional questions.